Hi Year 10. In this YouTube tutorial video, I'm going to be focusing on focus 3 of your milestone task, which is building earthquake-proof structures. There's a number of different ways you can earthquake-proof a structure. So I'm going to go through a few of those different ways with you now in this tutorial. And the first one I want to talk about is base isolation. But before I do that, I'm just going to show you what focus 3 looks like in your milestone task. Focus 3 can be found from pages 5 through to 10 of your milestone task, and it starts off looking like this. Building earthquake-proof structures. So you need to design and build an earthquake-proof structure based on your understanding of how earthquakes work and some of the different ways we can actually earthquake-proof a structure. So your design brief starts by saying you are an engineer who has been tasked by the New Zealand government to help design the new buildings that will help to rebuild Christchurch after the 2011 earthquake reduced much of the city to rubble. They have asked you to design and test the structures so that they can be sure the new buildings will stand up to any future earthquakes. The government has given you the following guidelines to help you design your initial concept. When you design your building, it must be at least 30 centimetres tall. It must contain at least one triangle, at least one square. There must be evidence of cross bracing to reinforce the structure, and you must include at least one other stability feature. You may cut and change your resources to fit your design. Now, in your packages that you got sent home with your milestone tasks in them, you would have also received a little bag that contained all of these things that looked like this. These are your resources to build your earthquake-proof structure. You should have some plasticine in there, which you can use to secure your structure together, paddle pop sticks, toothpicks, some styrofoam balls, some black bendy straws, and some pipe cleaners. Those are the only resources you are allowed to use to build your earthquake-proof structure. So that could be a fun challenge for you guys. The next step is to complete your design brief to actually test and build your structure. You are going to need to come up with a really cool company name here. It can be any sort of company name you like. This is your task. Come up with a really cool company name as the builder of these earthquake-proof buildings. So the problem that needs solving, I'm going to throw you a bone with this one. The problem that needs solving is that you need to create structures that are going to be earthquake-proof to try and reduce the cost and potential of lives taken when another earthquake happens in Christchurch. So that's why we want to build these earthquake-proof structures, because one, it will save lots of money because they don't have to rebuild things all the time, and two, it will save lots and lots of lives if people are not being crushed inside crumbling buildings when there's an earthquake. So that is the problem that needs solving. Then you need to mind map some solutions. So what are some ways this problem can be solved? And that is with what we're going to go through in this tutorial, talking about different ways we can earthquake-proof structures. So what are some of those ways we can earthquake-proof our structures? Then you need to identify for me which of these earthquake-proofing solutions you are going to use in your structure. Will you use cross bracing, base isolation, tapered geometry, counterweights, or a combination? Or have you researched something else that's really cool and have you come up with something that we haven't talked about in this tutorial? The sky is the limit with this one, guys. I want you to come up with a structure that is awesome and unique and that works really, really well for saving that building from earthquakes. And lastly, how will you make your structure strong and reduce the effects of earthquakes? So that is your initial mind map before you start designing. Then you're going to go into your design plan. I would like you to find some other designs as inspiration and create a collage of those designs. You can do this on the printed page or you can do a digital version. It's completely up to you. Then I would like you to draw and label your initial design. I'd like you to draw and label this before you start building because it will give you some clear guidelines to work with, and then you'll know what resources you actually need to use and where you can potentially use others elsewhere. Once you have made your design, you get to test it. You can test it out at home, pop it on a table, give it a shake. Have you made your own shake table somehow? That would be pretty cool. There's lots of great YouTube tutorials on how you can make really simple homemade earthquake shake tables. So if you're super clever and you've managed to do one of those, that is amazing and I would love to see it. So I want you guys to test it out. Then I want you to list the things that worked really well to protect your building and list some of the things that you might change to make it more stable. Draw and describe your test results, please, guys. This is really important. In science, when we do scientific experiments, our results are the most important part of our scientific experiment. They're the things that we analyze. That's how we get our results. That's how we know what is actually going on in our experiment and how we might be able to change it up next time. So please make sure you draw or describe what you got from your results. Did your building fall down? Did it crumble? Did some of it stand and some of it fell down? What actually happened with your test? Then I would like you guys to go ahead and improve on your design. So on improving your design, you're going to use the feedback that you took from up here, listing the things which you would change to create more stability. What would you change? Go ahead and change it. This is how you improve your design. So go ahead and do a second design that you think should be more stable and then retest it and see what happens. Test your second design on your shake table. Draw and describe your results. So whatever happened, happened. You need to draw or describe exactly what happened in your second test. It might have made it more stable, in which case that's amazing, but it might have not been more stable. You might have got the same results as before, or you might have got worse results than before. And that's okay too, because when we're doing science, we are just looking to see what happens. We're not looking to get a particular result. We're just testing what happens in our scientific experiment. So very important for you guys to draw and describe your results on your second test to see how your stability worked out. You're going to reflect on that second test. So list the changes which worked well to improve the stability of your building and describe how these changes changed the stability. So how did they actually work to make your building more stable? And that is it, guys. That's the last part of your milestone task. So let's go back to our PowerPoint here and we'll go through some of those different ways that we can actually earthquake-proof a structure. You are not restricted to the ones that I go through today. If you do some Googling and you find another really cool way to earthquake-proof your structure, that's incredible. I would love to see that. So don't feel like you're restricted to what I've put in this PowerPoint slide. So focus 3 is found on page 5 to 10 of your task. Here are some YouTube resources that you can use to help you understand base isolation, which is our first earthquake proofing concept we're going to go through. And again, you guys can find those on my YouTube channel, which is Skillset Dubbo Offsite Learning with Rach. And you can find those in your Building Earthquake Proof Structures resource videos. So you can see base isolation videos right there, ready to go, ready to watch for you. Okay, so what is base isolation? You can see there's a small animation here. Basically, the building is constructed on top of flexible pads that isolate the foundation from the ground, so that when an earthquake hits, only the base moves, while the structure above it remains steady. So these little pillars here are flexible, and those pillars are actually attached to the ground, but the building is not attached to the earth other than by these flexible pillars. So what you can see here is you can see that the base here that's attached to the earth moves, but these flexible pillars allow that building structure to stay quite steady, which is really, really cool. So here's another little picture that we can see. And you can see that when the building is attached directly to the ground, it creates a lot of movement in that building. But when the building is on top of these flexible pillars, which are attached to the ground, there's much, much less movement in that building. So what you will find is the buildings will be more stable and less likely to crumble or fall down when an earthquake actually hits. So that's base isolation. Go ahead and have a watch of these really great YouTubes. They've got some excellent information and animations in them that you can use for your understanding. Okay, the next one I want to go through is building earthquake-proof structures using tapered geometry, and it pretty much speaks for itself. If you have a look at these pictures, you can see really well. Tapered geometry just means that the structure, such as its shape, its diameter, and its geometry, tapers or gets larger or smaller as a building gets taller. There's a really good example in the picture just there. So you can see from this image that the effect that the narrowing has on the distribution of the earthquake waves. We can see down here, this is a seismic reading. It measures how much the earth is moving or how much the building is moving when an earthquake has actually hit. So down here at this really wide base, we can see this is the movement that's actually being recorded in the building. But as we get higher and higher and higher up to the 21st, 29th and 49th floors, there's a lot more movement in that building. So if we use tapered geometry, it's basically funneling all of those waves and all that movement up into the point, and it's less likely that that building is going to topple or be damaged by that movement because those waves are being distributed throughout the building. So the base experience less impact from the earthquake waves, and as such, it can remain more stable. So that's tapered geometry. That might be something that you want to include in your design. Okay, our next one that we'll focus on is cross bracing. Cross bracing is really cool, and it's an easy thing you can do. It can help strengthen the structure against the violence of earthquake waves by just providing more points for those waves and that energy to be absorbed. So notice the difference in these two structures on the left. One which has cross bracing, you can see here it's got that cross bracing into the center, and one which does not have cross bracing. So even just from this simple picture, we can see that this structure here is much more stable than this one over here. So if an earthquake struck, which one do you guys think would stand up a bit more to that earthquake movement? And cross bracing is one of the things that you must include in your building structure. It's in your criteria for when you do your build. So really good one that you need to include and have a good understanding of how it strengthens a structure. And the last one I'm going to talk about is using a counterweight. So counterweights can be really cool. There's a really great YouTube video for this, again, which is on my YouTube channel, ready, sitting there, waiting for you guys to watch and enjoy it. If you want to cut the time down, because it waffles on a bit, so if you want to cut the time down that you're watching the YouTube, just watch from 1:15 to 3:05. It'll give you a really good explanation and visual of how these counterweights work. So counterweights can help to balance the building and counteract the movement caused by the earthquake waves. You can see even just from this picture here that when the base is moving, the earth is moving, this counterweight also moves from side to side and helps keep that building straight and tall and centered and balanced. Without the counterweight, there's quite a bit of movement side to side in that building, which you can imagine would be really bad for an actual building if an earthquake hit. This is an example of a very, very tall structure which has that counterweight in there to help counteract the effects of earthquakes and stop it tumbling to the ground and killing hundreds or thousands of people and costing probably millions and millions of dollars to fix. So that is the end of your milestone task, everyone. I hope that you have gotten a lot out of these tutorials. If you do have any questions, please feel free to comment in the YouTube comments or on Facebook, and I will answer any questions that you have. And please post photos of your incredible builds, because I would love to see them, and I would especially love to see them as your earthquake hits. Let's see what happens. Let's see who can create these fantastic, strong, earthquake-proof structures. All right, I hope you guys have a fantastic day, and hopefully I will see you soon.